Now we're going to cover the topic of vector subtraction. I'm going to make a statement about how to subtract vectors. And the statement is this: to subtract one vector from another, instead add the inverse vector. To subtract one vector from another, add the inverse vector instead. Now, this is not such a strange idea as you might imagine, because we do this with normal numbers all the time. For example, if we subtract 6 minus 8, we know the answer is minus 2. But instead of subtracting 8, we could add minus 8. So we now have 6 plus minus 8, which is also minus 2, of course. So that's all we're going to do. Add the inverse vector instead of trying to subtract the vector directly. Let's go back to our diagram with just two vectors, A and B, from the last movie. In this diagram, I need to draw the vectors a little smaller, otherwise we're going to be off the screen. Last time we added vector B to vector A by simply drawing another vector B from the end of vector A and drawing in the resultant vector. Now, as we're going to find A minus B instead of A plus B, first of all, we need to find the inverse of vector B. Well, that's easy enough. We know from our previous work that the inverse of vector B is simply the vector that is the same length as vector B and parallel to it, but the points in the opposite direction. So here is our vector minus B, the inverse of B, and we can now dispose of vector B itself. What we need to do now is to move the vector minus b so that it joins onto the end of vector A. But first I need to move vector A a little to give us some room. This is perfectly okay, of course. You know by now that we can move vectors about as we wish, because all vectors that point in the same direction and are the same length are equal vectors. Now put the beginning of vector minus b right on the end of vector A. So along vector A and then down vector minus b is the high road. And the low road is the direct route from the beginning of vector A to the end of vector minus b. And it's as simple as that. But what about the sum vector A minus vector A? In other words, can we take a vector from itself? To do this, we do exactly the same as we did with vectors A and B. We add the inverse of vector A to the original vector A. So here's vector A and here's vector minus A. We move the minus A vector until the beginning of it coincides with the end of vector A, just as we did before. This means, of course, the vector minus A lies exactly along vector A, but in the opposite direction. So the high road is along vector A and then immediately back along vector minus A, and obviously cancels it out. So the low road doesn't go anywhere. We finish where we started. It's rather like standing at the North Pole and going north. You don't go anywhere. So what's the resultant vector? Well, we have a vector that has no length and doesn't seem to point in any particular direction. We call this vector the zero vector. Sometimes it's called the null vector. What a crazy idea, you might think, to have a vector that has no length and no particular direction. But think about normal numbers for a moment. How could we answer the question 10 minus 10 if we didn't have the concept of 0? And it's the same with vectors. If we don't have the concept of a zero vector, how can we answer questions such as vector A minus vector A? And what symbol do we give to the zero vector? Well, we write a 0 either in bold for printed text or with a squiggle for handwriting. Without the bold or squiggle, it would just be the normal number 0 and not a vector. This all raises an interesting situation. When we have a series of numbers to add and subtract, such as 14 minus 8 plus 6 minus 10 minus 3 plus 5, it doesn't matter which order we do these in, as long as we always subtract the 8 and add the 6, etc. We'll always get the same answer. Surprisingly, perhaps, it's the same with vectors. If we have a string of vectors to add and subtract, such as a minus b plus c plus 2a minus b, we can do them in any order as long as we keep the right sign with the right vector. Now we can go back to our original hexagon again and fill in the gap from the addition movie. You'll remember that we had this diagram and we saw that there were two high roads leading from F to B. The one from F to A and then from A to B we dealt with and obtained the vector A plus B. Well, now we're in a position to look at the alternative route of F to E to D to C and on to B. First, we fill in the missing vectors on the hexagon. You'll remember that because ED is parallel to AB and goes in the same direction, the vector ED can also be written as a small b. Similarly, vector FE is C and vector DC is A. So going from F to E to D to C to B gives us the high road vector C plus B plus A minus C. But we know now that we can work these vectors in any order, providing we keep the right sign with the right vector. So we can think of this as C minus C plus B plus A. And we know now that C minus C is the zero vector. In other words, minus C cancels out the C. So we are left with B plus A. But B plus A is the same as A plus B, giving us the same low road as before. In other words, the same resultant vector. Do you need convincing that B plus A is the same as A plus B? Well, we can see this from this diagram. The top high road is the vector A plus B, and the bottom high road is the vector B plus A. But they both start and finish in the same places, so they both give us the same low road, the same resultant. Therefore, in vectors, A plus B equals B plus A, and that's worth remembering. Again, it's just like normal algebra. The point of all this is that if you go from one point on a diagram to another point, such as from F to B, as in this problem, it doesn't matter which way you go for the high road. The low road will always work out to be the same. Any extra vectors will simply cancel out as the C's did in our example. And this is a very powerful idea, as we shall see, and it allows us to do all sorts of amazing things with vectors. So, in summary, 1, we can subtract one vector from another by adding the inverse of the second vector. 2, there's a vector called the zero vector, or null vector, which helps us answer questions such as vector A minus vector A. 3, if we're going from one point on a diagram to another, it doesn't matter which way round we go for the high road, the resultant vector, the low road, will always turn out to be the same vector. 4, we can add or subtract a string of vectors in any order, providing we keep the right sign with the right vector. And number 5, two vectors can be added in either order. So A plus B is the same as B plus A, just as with normal numbers. The same is not true of subtraction, however. A minus B is not the same as B minus A, and that's the same as normal numbers too. As you know, 8 minus 6 is not the same as 6 minus 8. Finally, as we have added vectors, subtracted vectors, and multiplied vectors by scalars, just normal numbers, you might well be wondering if it's possible to multiply or divide vectors by vectors. Well, it is possible to multiply vectors by vectors. In fact, it's very interesting because there are two different ways of doing it, but you do not need to worry about that at GCSE level. And as for dividing vectors by vectors, well, believe me, you just don't want to go there. Well, not this year anyway.